On the edge of the Giza Plateau, beneath the shadow of a structure that has stood for 4.5 millennia, we often look with a sense of wonder, assuming the methods of its creation are forever lost to time. We see the sheer scale, the precision, the weight of stone, and conclude that ancient hands must have possessed secrets beyond our grasp. The modern world, with its steel, its composites, its computational power, sometimes forgets that the fundamental forces of engineering, load, leverage, friction, tension, have always been the same. What if the blueprints for some of our most advanced machines, our most resilient structures, were sketched not in CAD software, but in sand and papyrus thousands of years ago? What if the answers to some of our contemporary engineering challenges were, in fact, ancient solutions, simply rediscovered? Today, we decode 7 ancient engineering secrets that modern engineers still rely on, principles born of necessity, refined by generations, and proven by structures that endure millennia. These aren't just historical curiosities, they are foundational truths, quietly at work in the world around us, from the deepest tunnels to the tallest skyscrapers. We begin with number 7. Imagine a desert landscape, shimmering under the relentless sun. Water is life, yet surface rivers quickly vanish, evaporated or absorbed. For centuries, civilizations withered without reliable water sources. Then, across the arid expanses of Persia, a solution emerged, the qanat. These aren't canals, they are underground aqueducts, often stretching for tens of kilometers, subtly sloped to tap into mountain aquifers and guide water through gravity to distant settlements. Each qanat begins with a mother well, sunk deep into the water table, then a series of vertical shafts are dug along the proposed route, allowing workers to excavate a gently sloping tunnel, sometimes just wide enough for a single person. The genius here is twofold: constant, cool temperatures underground minimize evaporation, and the consistent gradient, often just 1 meter of drop over several kilometers, ensures a steady, low-velocity flow, preventing erosion. Modern engineers use this same principle of low-gradient underground flow for critical infrastructure. Consider the city of Los Angeles, a sprawling metropolis in an arid region, fed by a massive network of aqueducts. The Colorado River Aqueduct, for instance, spans 242 miles, carrying up to 1 billion gallons of water daily, much of it through tunnels and covered conduits that mimic the qanat's efficiency by minimizing evaporative losses. And the largest storm drains beneath cities, those vast subterranean rivers designed to prevent catastrophic flooding, operate on the same gravity-fed, low-gradient principle, moving millions of gallons per hour. The trick is maintaining that precise, almost imperceptible slope over vast distances, a challenge of surveying and earth-moving that the ancient Persians mastered with remarkable accuracy using rudimentary tools. Their qanats, some still functioning after 2,500 years, demonstrate a passive water management system that modern civil engineers still strive to replicate for resilience and sustainability. Coming in at number 6. Picture a Roman builder, standing on a construction site, observing his laborers mixing ingredients. Not just lime and aggregate, but something special, volcanic ash. The result wasn't just mortar, it was a miraculous, self-healing material. This was Roman concrete, a substance so durable that structures like the Pantheon's dome, with its staggering 43.3-meter unsupported span, have survived 19 centuries. The secret wasn't merely strength, but resilience. This concrete, specifically using volcanic ash known as pozzolana, forms a binder called calcium aluminate silicate hydrate. When cracks appeared in older Roman concrete, rainwater would seep in, reacting with unreacted lime particles and the volcanic minerals to form new calcium carbonate crystals. These crystals would expand, naturally filling and sealing the microfractures. It was, in essence, a living material. Modern material science is now actively rediscovering and engineering self-healing concrete. The European project Healkin, for instance, developed concrete with embedded capsules containing healing agents or bacteria that produce calcium carbonate when exposed to water and oxygen. This isn't just about extending the life of structures, it's about reducing maintenance costs for massive infrastructure projects, from bridges to coastal defenses. Consider the Øresund Bridge, connecting Denmark and Sweden. Its concrete elements are constantly exposed to corrosive saltwater and the freeze-thaw cycle. While not self-healing in the Roman sense, engineers continuously research and apply advanced concrete formulations to resist such stresses. The ability for a material to repair itself, whether by ancient mineral reactions or engineered bacteria, is a holy grail for reducing the carbon footprint and lifespan of our crucial infrastructure. The Roman engineers weren't just building, they were growing their structures, an insight we are only now fully appreciating. Number 5 on our list. Imagine a workforce of thousands, straining to move colossal stone blocks, some weighing upwards of 200 tons, up the side of a massive pyramid. How did they do it? The conventional image of long, straight ramps is often cited, but the sheer volume of material required for such ramps, and the incredible gradients needed, makes them impractical for the upper levels. The actual trick, recent archaeological findings suggest, involved a sophisticated system of switchback ramps, often built against the pyramid's core, utilizing friction and leverage in ingenious ways. A discovery at Hatnub, an ancient alabaster quarry, revealed a ramp system with staircases flanked by numerous post holes. These posts would have allowed the use of ropes wrapped around them, creating a mechanical advantage for pulling heavy sledges uphill, significantly reducing the effective force required from each worker. It was an ancient system of pulleys and winches, but using static posts for leverage. This principle of leveraging friction and fixed points to move immense loads up steep inclines is vital in modern heavy lifting. Take, for instance, the construction of massive offshore oil platforms, where modules weighing thousands of tons must be lifted or slid into place. While modern cranes use hydraulic power, the fundamental physics of managing load and friction, often with multi-part line systems and guide rails, echoes the Egyptian solution. The launch of the USS Gerald R. Ford aircraft carrier, a vessel weighing 100,000 tons, involved careful control of friction and guided movement down a slipway. And in mining operations, conveyor systems carrying millions of tons of ore uphill over vast distances use complex drives and idlers to manage the cumulative force, a direct descendant of understanding how to apply and manage force against friction to overcome gravity. The Egyptians understood that moving things was not just about brute strength, but about intelligently distributing and multiplying force. Which of these ancient solutions do you think had the biggest impact on the daily lives of the common people? Tell me below in the comments. At number 4. Walk through a Greek temple like the Parthenon, and notice the vertical grooves carved into its massive columns. This isn't just decoration. This is fluting, a subtle design choice that serves multiple engineering purposes, many of which remain relevant today. First, fluting disguises the joints between individual drum sections of the columns, making them appear monolithic and taller. But more importantly, it visually enhances the perception of verticality and slenderness. The play of light and shadow within the flutes makes the column appear more refined, less bulky, and corrects the optical illusion where plain, massive columns can seem to bulge or appear concave at the top. From a structural perspective, while the flutes remove some material, the remaining ridges provide stiffness, somewhat akin to corrugation in a cardboard box, adding a subtle resistance to buckling. This blend of aesthetics and subtle structural enhancement is common in modern engineering, particularly in architecture and product design. Think of the rib designs often found on the exterior panels of modern skyscrapers, like the Burj Khalifa. These vertical lines, while aesthetically pleasing, also break up the building's visual mass, make it appear taller, and can contribute to wind load distribution by creating turbulence. Similarly, the reinforcing ribs often found on aerospace components or the internal structure of large castings aren't just for strength, they also manage stress concentration and can make parts appear lighter or more elegant. The fluting of a column, in its simplest form, is a form of engineered geometry that optimizes both visual perception and structural performance, a principle that dictates everything from the shape of an aircraft fuselage to the profile of a modern train. Holding the third spot. Imagine the Andes Mountains, a landscape of steep slopes and torrential rains, where agriculture seems impossible. Yet, the Inca civilization thrived, supporting millions with vast agricultural output. How? Through terracing. These weren't just simple steps, they were sophisticated, multi-layered systems of stone walls, carefully engineered drainage, and specific soil compositions. Each terrace acted as a small, flat microclimate, trapping heat, conserving water, and preventing erosion on slopes that could exceed 45 degrees. The retaining walls, often built with dry stack masonry, were permeable, allowing water to slowly drain rather than accumulate and destabilize the structure. The layers of gravel, sand, and topsoil within the terraces also filtered water and regulated temperature. This ancient solution to erosion control and sustainable agriculture is now seen as a cutting-edge approach in modern civil engineering and environmental management. Modern engineers design sophisticated stormwater management systems that use similar principles. Instead of channeling water away rapidly, which causes erosion and downstream flooding, green infrastructure projects incorporate terraced bioswales, rain gardens, and step pool systems. These mimic the Inca's approach, slowing water flow, allowing it to infiltrate the soil, and filtering pollutants. For example, the steep slopes around modern highways or new developments often use geocell confinement systems, essentially a modern form of terracing, to stabilize soil and prevent landslides. The Inca didn't just farm on mountains, they engineered the mountain itself to farm, creating resilient, self-sustaining ecosystems that are a masterclass in land management. At number 2, we find a structural masterpiece. Cross the Zhaozhou Bridge in China, built over 1,400 years ago, and marvel at its elegance. It's a single segmental arch bridge, with an unsupported span of 37 meters, built not with a continuous arch, but with 4 smaller relieving arches carved into its spandrels above the main arch. This isn't just aesthetic, it's an ingenious engineering solution. These smaller arches reduce the dead load on the main arch by 15 to 20%, making the bridge lighter and requiring less material. They also allow floodwaters to pass through more easily, reducing hydrodynamic pressure during floods. This design creates a much stronger, more resilient bridge than a solid spandrel arch of the same span and material. The entire structure is held together by precise stone cutting and gravity, without mortar between the main arch stones, allowing for slight movement and reducing internal stresses. Modern bridge builders employ variations of this lightning principle extensively. The iconic Sydney Harbour Bridge, a steel arch bridge, uses a complex web of trusses within its arch to distribute loads and reduce material, rather than a solid plate. More directly, the concept of relieving stress and weight through internal voids or secondary structures is foundational in modern structural design. Pre-stressed concrete box girder bridges, common in highway construction, are hollow internally, reducing weight while maintaining strength. Even in aerospace, the internal structure of aircraft wings features ribs and spars that effectively create relieving arches within the wing, reducing weight without compromising the ability to withstand immense stresses. The Zhaozhou Bridge demonstrated that strength isn't just about mass, it's about intelligent distribution of forces and removal of unnecessary material, a core tenet of efficient engineering. And finally, at number 1, the enduring resilience of the ancient world. Stand amidst the ruins of Machu Picchu, or in the ancient streets of Cuzco, and examine the walls. You'll see massive stones, some weighing dozens of tons, fitted together with such precision that not even a knife blade can slip between them. This is Incan earthquake-resistant masonry, a dry stack construction method designed to withstand the frequent, violent tremors of the Andes. The stones are not only cut with extraordinary accuracy but often feature irregular, interlocking shapes, sometimes called polygonal masonry. The engineers understood that rigid structures shatter. Instead, their walls were designed to dance with the earth. During an earthquake, the interlocking stones could shift slightly against each other without collapsing, like a three-dimensional jigsaw puzzle. The slightly inward slope of many walls, a feature known as batter, also increased stability. This wasn't just building a wall, it was designing a flexible, shock-absorbing system. This fundamental principle, that flexibility and energy dissipation are key to surviving dynamic forces, is paramount in modern earthquake engineering. Skyscrapers in seismic zones, like those in Tokyo or San Francisco, don't just rely on rigid strength. They incorporate advanced seismic dampeners and base isolation systems. Base isolation involves placing the entire structure on flexible bearings, often made of rubber and steel, which decouple the building from ground motion, allowing the earth to shake beneath it while the building remains relatively still. The Taipei 101 skyscraper, for example, features a massive tuned mass damper, a 660-ton steel sphere suspended between floors, designed to swing in opposition to the building's sway during high winds or earthquakes, absorbing kinetic energy. Even the bolted connections in steel frame buildings are designed to allow a controlled amount of yielding and deformation, preventing brittle fracture. The Inca engineers, without steel or computational models, instinctively understood that surviving the impossible meant yielding, not resisting, the power of nature. They designed structures that didn't fight the earthquake, but moved with it, a lesson still fundamental to our most advanced resilient architecture today. We are surrounded by